There is a moment, early on a gray morning at a petrochemical construction site, when a reactor vessel the size of a 10-story apartment building is lifted clean off a set of transport trailers. The vessel weighs roughly 1,800 metric tons. It is made of thick alloy steel, packed with internal components, and it hangs in the air on steel wire ropes no thicker than a man's forearm. The crane doing the lifting is itself enormous, a ring of crawlers and lattice boom that occupies a circle of ground roughly 170 meters across. The whole assembly, crane plus load, represents something close to 20,000 tons of steel and counterweight pressing down on the earth. And yet the crane does not tip. It does not lean. It does not tremble. It simply lifts, rotates a few degrees, and sets the vessel down exactly where the engineers planned, with a precision measured in centimeters. The question is not how strong the crane is. The question is how it stays upright at all. Because here is the puzzle. When you hold a heavy bag out at arm's length, you feel the pull trying to rotate you forward. The further the bag is from your body, the harder you must resist. A crane is doing exactly that, holding a load far out from its own center, but the crane has no muscles. It cannot grip the ground harder. It cannot lean back. It can only use what it already has, which is geometry and weight, arranged in a way that most people would never think to look for. By the end of this, you will understand the exact trick these engineers use, and you will be able to explain it to someone else in one sentence. To understand the problem, think about what tipping actually is. It is rotation. When an object tips, it rotates about an edge. The front edge of its base becomes the pivot, the way a seesaw pivots about its center. For the crane to tip forward, the weight of the load and the boom pulling it toward the load side must produce a rotational force, engineers call it a torque or a moment, that is larger than the rotational force on the other side of that pivot. The side resisting the tip is the weight of the crane itself, and crucially, whatever is behind the pivot, which includes the counterweights. So tipping is entirely a question of torque balance. Torque is not just force. It is force multiplied by distance. A small force acting far from the pivot can easily overpower a large force acting close to it. This is the lever, and it is thousands of years old as a concept, but what these engineers have done with it in the last half-century is extraordinary. Here is the real mechanism. The crane's total center of gravity, the single imaginary point through which all of the combined weight acts, must stay inside the footprint of the crane's support structure. Always. If it drifts outside that footprint toward the load, the crane tips. The entire engineering challenge of lifting thousands of tons is simply this: keep that combined center of gravity over the ground that the crane is standing on, at every point during the lift and the swing. The way engineers do this, at the scale of the world's largest land cranes, is through counterweights. Not small counterweights. We are talking about masses of steel plate or water-filled tanks that can reach 1,500 to 2,000 metric tons on a single machine. On the Liebherr LTM series of crawler cranes and on large ring cranes, the counterweight is mounted on a separate ballast car or a ring that literally circles the back of the machine as the boom swings, always staying on the opposite side of the load. The counterweight does not just sit there. It actively repositions itself to balance the torque created by whatever is on the hook. Think of it this way. Imagine you are trying to carry a very long plank balanced on one shoulder. If you push the far end down and the near end up, you feel stable. If someone hangs a weight off the far end, you slide something heavy onto your near end to compensate. The ring crane does exactly this, but with hundreds of tons of steel on a circular rail, moving precisely and continuously as the boom rotates. The system is constantly solving a torque equation. Now here is where the obvious guess goes wrong. Most people, when they look at a giant crane, assume the secret is being heavy. They think the machine stays up because it weighs so much that it cannot possibly tip. This is incorrect. Raw weight alone tells you nothing. A tall, heavy machine with a narrow base can tip over just as easily as a light one, easier, in fact, because more weight above the pivot means more torque when it starts to go. It is not how much the machine weighs. It is where the weight is. Which of these machines would you least want to be standing next to at the moment something goes wrong? Tell me in the comments below. The engineers working on the Mammoet PTC ring cranes, which have been used on everything from nuclear power plant construction to offshore module installations, understood this completely. The PTC 200DS variant, for example, can lift loads approaching 3,200 metric tons. Its counterweight system uses a ballast ring that holds roughly 2,400 metric tons of steel. The crane's working radius, the distance from center to hook, can extend to around 100 meters. At that radius, even a modest load creates an enormous torque. The only answer is an equally enormous counterweight arm on the other side. The machine is not fighting gravity. It is using gravity on both sides of the pivot simultaneously, keeping the equation balanced. The ground itself is part of this calculation. The crawler tracks on large heavy lift machines distribute load across an enormous area precisely so that the ground pressure stays within what the soil can bear. Engineers carry out full geotechnical surveys before a large lift. They design crane mats, interlocking timber or steel platforms, to spread the load. On the Sarens SGC-250, which holds the record for land crane lifting capacity at roughly 5,000 metric tons, the load case on the ground has to be calculated for every position of the boom during every phase of the lift. The footprint is not just about staying upright. It is about not sinking asymmetrically, which would itself shift the center of gravity and destroy the balance. There is a subtlety here that engineers think about constantly, which is that the center of gravity is a moving target. As the boom slews, rotates horizontally, the geometry changes. As the load is raised or lowered, the geometry changes. As the counterweight repositions, the geometry changes. The crane is never in a single static state during a lift. It is passing through a continuous series of configurations, each with its own torque balance, and the design must keep the combined center of gravity inside the support footprint for every single one of those configurations, with a safety margin on top. This is why the planning for a major lift on a megaproject can take months. Engineers model every degree of rotation, every meter of hook height, every possible wind speed. The false belief, stated plainly, is this, that a crane capable of lifting thousands of tons must have some extraordinary, almost mysterious structural strength that ordinary engineering cannot explain. The reality is the opposite of mysterious. The crane stays upright because of a concept you can demonstrate with a ruler, a pencil, and 2 coins. Place the ruler on the pencil. Put a coin on one end. Put another, heavier coin on the other end, closer to the pencil. The ruler balances. Move the load coin out further and compensate by adding another coin on the near side. This is the engineering. The machine is just a very large ruler. What makes the giant cranes remarkable is not that they defy physics. It is that they apply physics at a scale and with a precision that took generations of engineers to make reliable. The Sarens SGC-250 was not designed in a flash of inspiration. It was the product of decades of learning from smaller machines, from failures, from near misses, from thousands of lifts where engineers watched carefully and measured what actually happened. Every feature, the ring counterweight rail, the crawler geometry, the hydraulic tensioning of the boom guys, the ground mat specification, exists because some earlier design revealed a gap in the thinking. And here is the single sentence you can use to explain the whole thing to someone else. A crane that size does not stay upright because it is strong. It stays upright because the engineers made sure the combined center of gravity, crane plus load plus counterweight, is always, at every moment, directly above the ground the machine is standing on. Everything else is just the machinery needed to guarantee that one geometric fact. The ground mat. The ring rail. The 2,000-ton counterweight moving silently around the back of the boom. All of it exists to protect one invisible point in space from ever crossing one invisible line. That is the engineering. That is the trick. And it has been hiding in plain sight on every construction site where one of these machines has worked, visible to anyone who knew what to look for. The bigger the machine, the simpler the trick that makes it work. Subscribe to see the hidden engineering behind the giants around you.